Okay, so after those couple of examples about Faraday's law, it I'd help if I had this in front of me. Couple of examples of things that work by induction. I already talked about generators. Another, today's vocabulary word is ubiquitous. Means something that's everywhere. Another ubiquitous device is a transformer. They're all over the place too. A transformer, as far as what it's used for, it's used to change voltages. At an electric generating station, what comes out of the generators is somewhat higher than you have in your house. I don't know exactly, maybe a couple thousand volts, something like that. But there's these great big transformers right outside the powerhouse where they step it up to a few 100,000 volts for long distance transmission. Of course, at the other end of the wire, if you bring hundreds of thousands of volts into somebody's house, you're going to electrocute all your customers, which is bad for business. So they step it back down. There's a substation where they bring it down to a few thousand volts, which is what they bring along the side of the road. The real high voltage lines are the ones on the metal towers. There's one that crosses, there's an east-west line a few miles north of Batavia here. I think you go under it before you get to Elba. I think it's, or is it the other side of Elba? Yeah. And it kind of skirts across the edge of Bergen and heads off. Anyhow, those big metal towers with the insulators that are about that long, those are the long distance transmission lines that are at really high voltages. The wooden poles on the side of the road, the insulators on them are only about this big because that's only a few thousand volts. There's a transformer right in front of your house that steps it down to the 120 volts that they bring into your house. And then inside the house, various devices need to change voltages. For example, if you go to charge your cell phone, if you have, I don't know, a 5-volt battery, what you charge a 5-volt battery with is something around 5 volts, probably a little bit more, but certainly not 120 volts. That sounds like a good way to make the battery explode. So inside that little thing that you plug into the wall to charge your phone, there's a transformer. Well, there's several things in there. There's a transformer in there to bring the voltage down to what you need, just a few volts. There's also some other stuff that converts AC into DC because house current is alternating current. But a battery is a direct current device. You need DC to charge a battery. But anyhow, that's what a transformer is for. As far as how you make one, you know, I've got one in the back. I'll go grab it. It looks a lot like that picture. So this isn't the charger off of a cell phone, but it's almost the same thing. It's a charger for one of those little handheld vacuum cleaners, you know, for when you don't want to vacuum the whole room, just the spot here where the stuff got spilled. And it died. And instead of just throwing it away, I took a hammer and chisel to the case. And so you can see what's inside. This stuff over here it's actually pretty simple, but the stuff on the circuit board here, that's what converts AC into DC. You've got a capacitor and 4 diodes. And the part we're interested in right now, close up for the camera here, that's a transformer. Of course, all the wires are broken from being handled too much, but these brown wires here used to connect to the 2 little prongs that, this is like trying to do something in the mirror. The 2 little prongs that that plug into the wall used to connect to these brown wires. They lead to what's called the primary coil. And then the wires that lead on from there used to connect. I think they've broken off entirely. But anyhow, if you want to see it closer, you can play with it for a while and then pass it on to the next person. But that's what's being shown in the picture here. Two separate circuits, okay? Primary coil, which is connected to your power source, and the secondary coil, which is connected to whatever the load is. In this case, it charges a battery. Both coils are wrapped around the same iron core. See, magnetic field lines like iron. They come down through there and then either loop back around on this side or loop back around on that side. Of course, it's an alternating current, so half a cycle later, everything points the other way. But the main point here is that the two coils have the same magnetic flux passing through them. The magnetic field lines created by the one coil also pass through the other coil, at least under ideal 100% efficient conditions. There wouldn't be any field lines escaping in between. So, as it says at the top of the next page, the voltage across each coil is the induced voltage from Faraday's law. Under ideal conditions, again, 100% efficiency, like that's actually going to happen, but under ideal conditions, the windings, the coils, have no electrical resistance. In the real world, they've got a few ohms, which is the reason transformers get kind of warm after a while. But for a simplified, idealized transformer, there's no electrical resistance at all. And so the voltage across each coil is the induced voltage from Faraday's law. And voltage across the secondary coil is the number of turns in the secondary coil times the rate that flux is changing through it. The primary coil not only induces a voltage in the other coil, it induces a voltage in itself. Any coil with a changing flux through it gets a voltage induced in it. No exceptions. So, number one induces a voltage in itself. The same magnetic flux passes through the other coil and induces a voltage in it. Let's take those two equations and divide the one by the other. When I do, delta phi over delta t drops out because it's the same flux going through both coils. And the moral of the story is that under these types of idealized conditions, which you can get fairly close to in reality, the ratio of the voltages is the ratio of the number of loops. If you want to take 120 volts and step it down to 12 volts, for example, then the primary coil could maybe have 500 loops, and the secondary coil would have 50. You've got a 10-to-1 ratio between how many turns in the coils. You got a 10-to-1 ratio between the voltages. Or you switch things around, you can step voltage up instead of down. So we've got a fairly straightforward problem here. It gives you 3 out of the 4 things in that equation and asks you to calculate the 4th one, basically. That's not the worst thing I've ever done to you. Part B might be a little trickier. I'll explain that after you've had a chance to think about it for a moment. Okay, not that much to this one. Part A. I think on the formula sheet, and also for that matter in the box there in the notes, I labeled them with 1 and 2 subscripts, or S for secondary, P for primary. Point is that the voltages are in the same ratio as the number of loops. Well, in this case, the question is how many loops should you have in the secondary coil to get the desired voltage if you're going to plug it into house current, 120 volts. Well, as I've probably said quite a few times by now, it doesn't matter. You can put the numbers in first and then do the algebra, or you can do the algebra first and then put in the numbers. I did the algebra first. On the primary coil, 1,000 loops. You want 5 volts on the secondary coil. You're plugging the primary coil into 120. Comes out 41 2/3. Well, yeah, getting 2/3 of a wraparound is probably a little on the, 42 is close enough. That'll step the voltage down for you by the desired amount. Part B. Instead of 120 volts of alternating current, typical house current, what if you got yourself 120 volts of direct current? You got 10 car batteries and you hooked them all, or 10 of the, I guess you can get 12 volt, like lantern batteries for when you go camping. But anyhow, you get 10, 12 volt batteries and you hook them all up in series, 120 volts, and you put that on your transformer. What are you going to get out? 0. Or the other answer I would have accepted is smoke. This is not something you should do to a transformer that you're fond of. But if you go back to Faraday's law, a transformer works by induction. Induction is caused by change. The change in the flux over the change in time equals the induced voltage. If you go back to how I derived this formula here, the one that I used for the example, that was derived assuming an alternating current, or assuming maybe not an alternating current, but some sort of changing flux. If you have a perfectly steady magnetic field, like you would get from perfectly steady direct current, you're dividing by 0 there. And the whole thing becomes invalid when you go back to how I derived that, okay? Change in flux over change in time is 0 if you have a steady DC field. So flux or induction works from change. The more rapidly things change, the bigger the induced voltage. If nothing is changing, nothing is induced. And well, just as a footnote, we're never actually going to be tested on, but the reason I said smoke is, remember that it's a self-induced voltage across the primary coil as well. What that does is it holds back the current through the primary coil. If you don't have that self-induced voltage, then all that's holding back the current is Ohm's law. And the person who designed the transformer tried to have as few ohms as possible for the internal resistance of the coil. So you put 120 volts on there, and you're probably going to get 20 or 30 or 40 amps going through. It's going to melt the insulation off the coil. So that's the thing with the smoke. But the answer to the question is 0. because changing flux it's a changing flux that induces the voltage on the secondary coil. Current in the primary doesn't change at all, and the flux it produces doesn't change at all. It's not the presence of a magnetic field that causes induction, it's change. Now, just as another little footnote, usually nobody knows, but once in a very great while, somebody does. How do they do it in a car? Because everything in a car is 12 volts. The sound system, the heater fan, the lights, it's all 12 volts DC except the spark plugs. If you're going to cause dielectric breakdown between the electrodes on a spark plug, I already talked about that several weeks ago, you need a high voltage to throw a spark through the air like that. And I don't know exactly what voltage they use, but it's high. It's well into the tens of thousands, like 50 or 75,000 volts. So the ignition coil in a car is basically a transformer, but cars are DC. So how do you get the ignition coil to work? There's nothing in Faraday's law that says that the current actually has to turn around and flow the other way. It just says it has to change. So what they do in a car is they turn the current to the primary coil. They turn it on, they turn it off, and they turn it on, and they turn it off. And so the flux from the primary windings builds up and collapses. But now, so this is another case where if you're familiar with obsolete technology, it's clearer than the modern black box way of doing things. Up until somewhere in the mid-1970s, cars had what were called points, or the full name was breaker points. Down inside the distributor, there were two little metal contacts. As the engine turned, there was a cam that made them close and open, close and open. Close. It's a mechanical switch. And what it was doing, it was turning the current to the ignition coil on and off, and on and off, and on and off, and on and off. And this was a routine maintenance item, just like changing the oil. Every 15,000 miles, you were supposed to change the points, plugs, and condenser, which is an old-fashioned word for a capacitor, okay? Well, in the 1970s, they came out with the solid-state ignitions, which instead of having to replace the point, because the points got all burned up, you know, they get all pitted and oxidized, and you had to put new ones in there. And now they do it with a transistor instead of with a mechanical switch, and that lasts the life of the car. But, you know, so it's better. But like all more sophisticated technologies, it's better and it's also more obscure. The old stuff, you could look at it and see how it works. Now it's black boxes. But anyhow, that's how you do it. It's not that transformers don't work on DC, they don't work on steady DC. You have to chop it. And then you can get it to work that way. And that's what's done in a car. Self-inductance. It says, Faraday's law says an EMF is induced in any loop of wire with a changing flux through it. This includes the loop that created that flux in the first place. I already mentioned that in connection with the back EMF in the primary winding of a transformer. The same thing is true even if you just have a solitary coil. You know, there is no secondary coil. You start looking through electronic devices, and sometimes you'll see little coils soldered on circuit boards along with the resistors and capacitors and transistors and diodes and stuff that's on there. A little solitary coil like that, which is included in a circuit for the purpose of its self-induced voltage, is called an inductor. Okay? The voltage the voltage across that inductor, that coil, it's due to Faraday's law. If you make a few substitutions into Faraday's law, you get the equation with the box around it there. The induced EMF that a coil induces in itself equals minus L times delta I over delta T. The minus sign is the same minus sign from Faraday's law that I told you not to worry about because we're not going to get involved with the direction the current is flowing. L is a property of the coil called its self-inductance, measured in a unit called a Henry. It depends on how the coil is made. How many times does the wire go around? How many loops does it have? Factors like that. Its length. So the construction of the coil determines L. I is how many amps are going through the coil. So delta I over delta T is the rate the current is changing in amperes per second. A more rapidly changing current creates a more rapidly changing magnetic field, gives you a more rapidly changing flux, if you want to take it back to Faraday's law. And it says that in parentheses. So, let's see, this is the last thing in section 6. I'm not, like I said earlier, I'm not going to try and start section 7 today. I think you might as well go ahead and plan on quiz 7 getting moved up from, I'll write up a revised schedule and hand it out probably next time. But I think it probably makes more sense to test you on section 7 a week after I've gone over it rather than like 2.5 weeks. So quiz 6 will be on the original schedule. Quiz 7 will be moved up to just before spring break instead of just after. In the meantime, work on this. I'll go over it in a little while, whether or not there's anybody left in the room. I'm going to throw out a hint for part A. I've already figured that out. Part A doesn't have anything to do with that equation a little further up the page. It's just simply this. If the switch is left turned on for a long time, that means the current will reach a steady state. Now, to a steady DC, coil is just another piece of wire, okay? The induced voltage depends on delta I over delta T, the rate the current is changing. If you turn this thing on and come back tomorrow, by then, well before then actually, delta I over delta T will have become 0. The current, whatever it is, will not be changing. So in that case, all you've got is a 12-volt battery with a 1.2 ohm resistor across it, which is probably just the internal resistance of the coil, actually. And so part A is just Ohm's law. Part B is where you then have to use the equation just above the question to figure out what the self-induced voltage would be when you suddenly pull the switch open and the magnetic field suddenly drops to 0. Okay, number 7. As I said a few minutes ago, to a steady current, a coil is just another wire. Steady current, the coil is just another wire. Something is only induced if there is a changing current. So just Ohm's law. The battery provides 12 volts. You've got 1.2 ohms of resistance in the circuit, and so before you pull the switch open, there's 10 amps flowing. Part B. When you pull the switch open, that 10 amps drops down to 0 amps. But of course, nothing happens instantaneously. It takes a little time. And I mean, it might seem like the switch loses contact instantaneously. It's touching and then it isn't. But as it mentions down there with the answer, as you pull the switch away from the piece of metal it contacts for a moment, there's enough voltage induced here to throw an arc across the space in between. So there's a brief transition period, well, and here it says 100th of a second. It realistically might even be shorter than that. The magnetic field does not go away instantaneously. It drops to 0 over a small fraction of a second. And during that brief period, a voltage is induced given by minus L times delta I over delta T. The rate the current changes times the coil's inductance. 0.6 of a Henry, which is a pretty good sized coil, actually. That's a kind of a big one. Technically, delta I is negative because the current is decreasing. So there are situations where you might be tempted to say, I can't get a shock out of this circuit. That's only 12 volts. Yeah, sometimes, even though it's a 12-volt battery, there are ways you can get a shock off of it. 600 volts would be, could possibly be a little on the dangerous side. See you next week.